All right. Let's take a look at this. All right, so we have the two visuals that we did prior to this page that might help us. The first visual represents set P, because our Celtic's name is the first component in each component of a domain is the name of the Celtic, and each component in our range is their height. And then this second picture represents set H, which is the heights first and then the names. So which of these ordered pairs represents a function? Let's help out with that one. Austin? Set P, okay. So set P, for each name, there's one and only one height for each name. So that certainly fits. And if we were checking out H is, let's see, for height 6 feet 2 inches, there's one name. 6'5", there's one name. Oops. But 6'9" has two different outputs. So that's why H is not a function. So what's my answer for B then? Does everybody agree with that? You thought it was both, and it is, because a function is also a relation. So H and P are a relation, because a relation is just a set of ordered pairs. Okay. No special conditions are placed upon it. All right. So just anything you're going to see, anything I give you is going to be a relation. You're looking for that special relationship of one and only one output for each input. Excuse me, each input has one and only one output to be a function. It's important in the order that you say it. Okay. So let's do this first one together. And then you can try the other three. So let's take a look at this first picture here. We've got three people, Phoebe, Amy, and Katie. That's our domain. And so let's write that down. A domain, remember, is a set, so you always write braces here. And you write the three inputs, Phoebe, Amy, and Katie, in any order you want. And the range is two outputs, 5 feet 5 inches and 3 feet 1 inch. Okay, so does this represent a function? Is there one and only one output for each element in the domain? For each name, is there one height? Does Phoebe have one height? Does Amy have one height? And does Katie have one height? So is this a function? Yes, it is. Okay, so you've got three more. You've got another pictorial representation, and the other two are sets represented by ordered pairs. So work these out in your group. When you all agree, put up your flag. Table number 2, would you tell me what you got for this second representation here? Is it a function? Yes, it's definitely a function, because for each element of the domain, it goes to one and only one output. So it's definitely a function. And what does the domain look like, CJ? All right. And what about the range? 7. All right, good. Any questions on that? All right. Now we have a set of ordered pairs. Does this table 3, that's Jonah and Setov, does this represent a function? Yes, absolutely. And what do we have for the domain here? All right. And Septa, what would the range be? Okay, but how many times? Yeah, just once. So 2, yeah? Yep, that's it. 3 different members of the second component, or the range, right? We don't have to list them as many times as they appear. And finally, the last one, table 4. No, and why is this not a function? Right, 3 goes to 7, and 3 also goes to -4. That's not allowed, right? So our domain, what do we get for the domain here, Amy? Okay, and the range, William?
7, 2, 5, 4.
Okay. All right, now I'm not sure, but if my math lab asks you to represent the domain and range like this, they're probably going to want you to do like smallest to largest. So just be aware of that when you put your answers in. Okay. So what happens now, we're going to take a look at the graphs of relations and functions. We were just looking at the set of ordered pairs and trying to determine whether something was a function. Now we're going to look at the graphs, because really most of the functions we're going to look at will either be graphs or models or equations or formulas. That we're not going to be like looking at a lot at names of Boston Celtics with their heights. They're really going to come in one of these forms. So here's a graph of a relation. It's definitely, I can always say it's a relation. Now we're trying to determine if it's a function. So first of all, let's find the domain and range of the following relation to determine if it's a function. So what would the domain for these 5 points be? What would the domain look like? And how would you find it? You want to mark the points on the graph, and by marking the points on the graph, she means find the coordinates. So let's find the coordinates of all these points, and you do it and I'll do it, and hopefully we'll have 5 sets of ordered pairs that match. So hopefully I won't mess up, and hopefully you won't. So you can check yours with mine after you're done. I know it is. It's a little tricky. Let's see, did I start up the recording again? Got to keep checking this since I forgot earlier. Yay! Woohoo! It's going. All right. All right. So what's the domain here for this particular relation? I don't know if I can call it a function yet. Seth, what do we have for the domain? And 1. And what do we have for the range? Gina? Yeah. 4. Okay. So the minute you see something like this, if you list it like this, notice you have 4 elements in your domain. How many elements are in your range? 5. You have more elements in your range than you have in your domain. That's a problem, because it means one of those elements in your domain must be pointing to 2 different elements in the range. And can you see which element in the domain has 2 different outputs? 1, right. 1, if we look at it as an ordered pair, from our graph, we have 1, 4, and we also have 1, negative 2. That's a problem. That makes this not a function. It's not a function since we have 2 outputs, 2 different outputs. For 1 has 2 outputs. Okay? That's not allowed. All right, if we're going to be a function. It's okay if you're a relation. You know how we all have relations, right? We sometimes don't want to admit some of them are relations, right? They may be functioning or non-functioning very well. I'm just trying to make up a silly story. All right. Now, if we were looking at this picture of these 5 ordered pairs, would there be a visual way to tell that this was not a function? And you're shaking your head, Amy. What do you say? Gina, sorry. Well, did you read ahead, or did you know about the vertical line test? You did. So the vertical line test, right? If you drop a vertical line, let's find a line here. If you drop a vertical line straight down through x equals 1, if I can get it right on there. Oops, I'm going to have to move it over a tiny bit. Let's see. Just to be, come on, get over there. I'm not going to, there we go. So if you drop a vertical line down through x equals 1, so the equation of that vertical line is x equals 1. That's the equation of this line. You notice that it hits 2 of those points. That means you have an input with 2 different outputs. So that tells you that this cannot, it's a visual check for whether a graph is a function or not. So let's take a look at what's coming up next. So this is a definition of the vertical line test. Notice this word right here is very important. If any vertical line, a lot of times when I ask students to define a vertical line test, they say, if a vertical line. Well, that doesn't work. It's not about one vertical line, it's any vertical line. So you have to imagine this like an animation with these vertical lines sweeping across from left to right. And if any vertical line intersects your graph in more than one point, then it's not a function. So we can see here that any vertical line as we go left to right here is going to intersect this particular graph in one and only one spot. Whereas if we sweep across this one, this vertical line hits it in 3 spots. So this is not a function. And this is a function. So what I'd like you to do now is at your seats, you have a couple of graphs, 3 different graphs. I'd like you to look them over. There's a little something different in each one, and see if, use your vertical line test to determine if it's a function. B is particularly interesting. Okay, the vertical line test to identify graphs of functions. So which one, A, B, or C, which ones are functions? A and B. Yes, yes, no. Okay. So if we look at C, the reason why we need to define a vertical line test as any line is because, and you know, this may seem like a picky point to you, but so math teachers can be picky. If I use the vertical line, which is your y-axis, if I just say a vertical line, that only hits that in one spot. Okay, so that's why you have to consider any vertical line that sweeps across this graph. And so this hits it in more than one spot, so this is not a function. This one again, any vertical line here is going to hit this in one spot. That's supposed to be a straight line. There's some way you can click, I think, click on these and make them straight, but other than doing this, but I don't remember what it is. I might be thinking of another software package. I am. Yeah, you're right. Paint, right, Paint does that. Okay, B often involves an interesting discussion. First of all, notice this first function. If I started with my pen right here, right, I could trace this function without lifting my pen off my paper, right? What happens if I do it for the second one? I get to here and then what? I have to lift my pen off. There's a gap here, and then I go like this. There's a name for that, and we call this, you don't really need to know this right now, continuous function, non-continuous. And what's happening here is, to define this function right here, I need 2 pieces. I need an equation that talks about all values of x less than 2, how I would graph it, and all values of x greater than 2. So I literally have 2 different equations. It's called a piecewise function to define this. And 2 is defined to be whatever this value would be. You could say that point's 2, 1. And it's not defined up here. That's why there's an open circle. So if you drop a vertical line straight down through x equals 2, it only hits this graph at one spot where it's defined. Let's call that point 2, 1. So this is a function. That's a little tricky the first time you see it. Okay, now if we go back to the very first equation or model we were looking at way back in lecture 1, you recall we were looking at a model that dealt with the cost, the average cost of tuition and fees at U.S. public colleges. And this is the equation that we used to model those costs. They didn't give us the actual data values, but it was the equation we used to model to predict or estimate what the costs would be. And we discovered that this was the best model. We could have used a straight line, but we decided on a baby parabola here to look at this. So we now, when we have an equation like this, which is what we're used to looking at, we have names for the x and y variables. X is free to be any number that fits this context. If, in other words, well, before, let's not look at the story yet. If I just gave you this equation, x could be any number on the number line, from negative infinity to infinity, any real number, and then y would be the corresponding real number. But because this has a story, there's an implied domain that you have to read and look at the story and think about. The value for x means it's the ending year after 2000. So recall, our data would look like this, right, with some cost. Blah, blah, blah. And what we would do is we would just take off the first part and look at the ending year, the year that ended, right? So it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all our non-negative integers. So the domain here for this particular function, based on the story and based on the definition right there, ending X years after 2000, the domain is all non-negative real numbers. And it's true for the domain. Well, the domain can't be non-negative. It has to be all positive because you can't get zero. There's no way to get zero here. Well, I shouldn't say that. I never tried to set that equation equal to zero. It would be some negative number. You should try it. But what we meant to say, the range. So the range could, let's see, real quick. How do I determine if the range could be zero? Well, I would set that equal to zero and I'd use the quadratic equation. Let's see what the discriminant of the quadratic equation is. Then I'd know a little bit about whether it's real or non-real. So let's see. B squared is 341 squared, which is some big number, times 4 times 4 times 3194. So 16. So let's take a quick peek. We'll just take a little digression. Let's okay. If we were just looking at this equation, there would be an x value that would make your college tuition and fees zero. Remember we did that with the GeoGebra project and it was model breakdown. But with this particular story, we start at zero. Our domain starts at zero. And if we put zero in for x, y is 3,194. Okay, it's the smallest value we have right now, 3,194. So we can say our range is all positive numbers. Now the question is, at what point does this parabola reach a maximum and then maybe start coming back down? So to be safe, we're just going to say the range is all positive real numbers. Well, up here we said integers. But these could maybe have cents on it, right? Dimes and pennies. So we don't know if they're integers or not. Okay. So the point here is we call the x values independent because we have a right to pick any year ending after 2000, 0, 1, 2, 3, 4. There's nothing preventing us from picking any of those years. But once we pick that value for x, y is completely determined. Okay, so we call y the dependent variable. It depends on whatever you put in for x into this equation. All right, so your book's going to give you a couple of homework problems like this, and they're going to say, test. Here's a little test to determine whether an equation represents a function. If we solve an equation for y in terms of x, and there are 2 or more values of y for a given x, then it's not a function. So we can't get 2 different y values for a given x. Okay, so if we look at this first function, this kind of threw my first class for a little, it took us a little bit to get to. If I asked you what kind of graph this would be if you were to graph this equation, what kind of graph would it be? What would the picture look like if you were to graph that? Everybody knows? Well, do you have to flip it around first? I mean, doesn't matter what order it's in. You could flip it around and that might give you. Okay, downsloping what? What's it called? Line. It's a line. It's a linear function. You see x to the first power. So this is a linear, well, right now it's a linear equation, right? We're trying to determine if it's a function. So if we put it into, as Jonas said, flip it around, what he means is put it into the more familiar form where we solve for y, then you can see the line like looking at you right in the face. So Daniel said a line that was a negative slope. Well, let's see if it's negative now. Let's solve this for y by subtracting 3x from both sides. So this is what you would do for your homework. And you get negative 2y equals negative 3x minus 12. And now you want to divide both sides by negative 2 to solve for y. So everything on both sides. So this gives you 1y, and this gives you 3/2 x. Subtract negative 6 becomes plus 6. Okay? So this is what you're more familiar with. This is the form of a straight line you're more familiar with, which is what we call the slope-intercept form. You see the slope and the y-intercept. Okay, but these equations are exactly the same. These two equations right here are exactly the same. They're equivalent to each other. So here you have one value of y for each x you pop in. So that's definitely a function when you solve this for y. So this is, yes, this is a function. Okay, let's do x squared plus y squared equals 16. Let's try to solve that for y. Hang on. What negatives? Where are we? Yeah, that's the same as 3/2. Yeah. So we subtract x squared from both sides. Negative divided by negative is the same as positive divided by positive, which makes life easy for us here. A little easy instead of looking at all those negative symbols. And now remember, this is to solve for y. We really would have to write, when we do the square root, the absolute value. But we know once we do the absolute value, we get a positive and a negative to solve it. So if we do this the right way, if we do this on both sides, we get the absolute value of y equals the square root of 16 minus x squared. The square root of 16 minus x squared. And that means y can either be positive 16 minus x squared, or y could be the opposite. So here's a situation where you have y equal to plus or minus the square root of 16 minus x squared. So if I put a value for x in here, right, like pick a value for x like 3, I get 16 minus 9, which is 7. So y, when x is 3, y is either the positive square root of 7 or it's the negative square root of 7. So I got two different outputs right here for the same value of x. So that makes this not a function, because you have two different y values for the same x value. Is anybody from way back in their mathematics, anywhere back in their brain, do you know what kind of picture x squared plus y squared equals 16 forms? Anywhere? Nobody knows? It's okay. I didn't really expect that you would necessarily know, but this forms a circle. And I can't draw a perfect circle, but it's a circle with radius 4, because if you take the square root of 16, it's 4. So you can get these points right away, and then you connect it with a circle. To graph something like this on your calculator, you set y1 equal to that one and y2 equal to that one. You get the top half of your circle, the semicircle, and the bottom half. So that's how you would graph a circle. Okay, but I'm not asking you to do that. I just wanted to show you. And you can see the vertical line test fails here, because if you drop a vertical line through anywhere through this circle, except for on the actual, these 2 points out here, you get two different outputs. Okay? This is not a circle. This is not a function. Okay? So you'll have a couple of questions where they'll give you an equation and they ask you to test whether it's a function or not. Okay, and this is how you do it algebraically. Okay, so the next thing we're going to do is look at functional notation. This may be new to some of you if you've never had functions before. And we're going to look at this same problem 3 different ways. We're going to look at it with a table of numerical values. We're going to look at the same function as an equation, and then we're going to look at the function as a graph. And we're going to figure out what this new notation means and how to interpret it. And then you're going to have a group activity to work on this. So here's, I hope something familiar to you. If we actually hit a baseball, over time, it's going to start at a certain height and it's going to go up in the air, reach a maximum height here, 103 feet above the ground, and then it starts to fall back to earth. Okay, so if we were to visualize that a few pages later, this is what it would look like as a graph. It starts off 3 feet above the ground. It increases in height until it reaches 103 feet, and then it comes right back down. So this is the graphical representation of that table that you see here. Okay, so let's look at notation. Since the height of the baseball is determined by how long it's been traveling, the time, we say that the height of the baseball is a function of the time. And so we're going to do away with the y equals notation from now on. In Math 107, we're going to use functional notation. So instead of using the variable y, we use letters. The typical letters that you see are usually little f, little g, a little h, big F, big G, big H. You could use S, you could use T, you could use P, but those are the standard letters that we use, at least initially when we're working with functions. So what we do now is we say that y is equal to f of x. That's how you say this, f of x. Y, the output. Y is an output value. So isn't this notation. They both represent the output or the second component in your ordered pair. It's the output. So now your ordered pairs are going to look like this, x, comma, f of x. F of x is just taking the place of the second output value in your ordered pair. Excuse me, of the output value, not the second one. It's the second component. Okay, now this notation does not mean f times x, because when you first learn algebra and you learn about parentheses with letters and numbers, you learn that that means multiplication, but not when you're dealing with functions. That just represents the output of your function. That's all it represents. Okay. So let's take a look at this table again, and you tell me what is the output value when I put 2 into this function. Well, I don't have an equation, so I have to look at my table. 2 is the input. 2 represents the input. That's like the first component in my ordered pair. And what would be the output that corresponds to 2 from looking at the table? What's the output? 99. There it is right there, 299. Okay, so f of 2, the value of my function when my time is 2 seconds is the number 99. That is the value of my function. So to interpret this, I would say at 2 seconds, I now use my number and my units. So I have to use the number 2 and the number 99 somewhere in my sentence, and I have to use the units that go with it. So at 2 seconds, the baseball's height is 99 feet, exactly, above the ground. So that's how I would interpret that notation. F of 2 equals 99 tells me that the baseball is 99 feet above the ground at 2 seconds. Okay. F of 0, what would my answer for that be? What is that equal to? What's the output? 0, 3, so what's the output there? F of 0 equals 3. Okay. And this tells me that my initial height, so I'm using a new word on you, my initial height of the baseball is 3 feet above the ground. And you say, wait a minute, Kavanaugh, you told us we always have to use the numbers. that are there. The ordered pair would look like this, 0, 3. I don't see a 0 anywhere. I don't see seconds. So that's all hidden right here in this word, initial. Initial is the word that we use when we're talking about at t equals 0 seconds in this case. You could also just do the same thing we did above. At 0 seconds, if you want to just play the game that way, the baseball's height, that's okay too. You don't have to be fancy and use initial if you don't want. Baseball's height is 3 feet above the ground. Period. So I'd like you to look at the next one and talk about it at your seats and write down your interpretation. It's a little different. Take a look at this. So this one's a little different because it's not asking for our output. We know what our output is. The output is 103 feet above the ground. So it's asking you to find the input. How many seconds have passed? So now you go to the table and you look along the first row until you find 103. Voila, there it is. There's 103. And you see that the corresponding time, that's its partner, is 2.5 seconds. So if you were to write the ordered pair here, it would be 2.5 seconds, 103 feet. So the height of the baseball will be 103 feet above the ground at 2.5 seconds. Any questions on interpreting this? Anything at all? Okay, so this isn't using interpretation when you're given, when you've represented your function as a table. Okay, now another way we can represent the same exact function is with this equation. But notice now I don't have y equals anymore. I have f of x equals. And notice what happens if x is 0. If x is 0, these first two terms disappear. And what's the height at x equals 0? 3. And that's the same as my table, 0, 3. Initially, that baseball was 3 feet off the ground. Now, that's either exactly where the batter hit the ball, 3 feet off the ground, or maybe we're playing t-ball and we have it set on a tee and we're hitting it 3 feet above the ground. So use the equation f of to find f of 2. So, and let's see if it agrees with our table. Our table was 2 comma what, 99? Was that our answer? Okay. So let's find f of 2. So 2 is the value of our input, which is our independent variable. Our independent variable, which is x. So we're going to substitute x equals 2 into our equation and find what our height is. So let's do that. F of 2 equals negative 16 times 2 squared plus 80 times 2 plus 3. And if you do out all your mathematics, you're going to get 99. All your arithmetic. Okay, well, this could get a little tiresome, so why don't I just put this function right into my calculator and look at my table, right? Why not? I mean, life is good. I've got this calculator. Might as well use it. Oops, not that way. X squared plus, what is it? 80x plus 3. And let me set my table. Well, my table's going to, oh, I squared 80 instead of putting an x in. Thank you. That would have definitely messed it up. Okay, there we go. Thank you. So let's set the table. We're going to start the table at 0 seconds, and we're incrementing by 1. And we could have it just work automatically. Boom. And there's my table. At 2 seconds, 99 feet. That works. Okay, so yep. Use the equation to solve f of x equals 99. Well, look, 99 is now our output. So if I were using my table, I see it has two answers, 2 and 3. So both at 2 seconds and at 3 seconds, I'm at 99. If I have two answers, that means to solve this equation, I'd be solving a quadratic equation. So let's see. My output is 99, so I replace f of x with 99. And I think we could use a little review of solving a quadratic. Why not? We subtract 99 from both sides to get 0 on one side, and we get negative 16x squared plus 80x minus 96. I don't know about you, I don't want to factor that, and I particularly don't want to put it in my quadratic equation. So is there any way I can simplify this? Well, is there a greatest common factor all the way across? And with a little bit of effort, I always try. We love factoring these second degree trinomials on the right side if we have 1 in front of x squared. So just check it out. Is negative 16 a factor everywhere? Negative 16 goes into 80 negative 5 times, and negative 16 goes into 96 6 times. So cool. So you can either factor it out, you can either factor out the negative 16, or you can divide each and every piece of your equation by negative 16. It doesn't have any variable in it. It's constant, so you're not losing any of your solutions. And now you get a nice little easy trinomial to factor on your right side. You can all factor that, no problem. And there are your two answers, x equals 3 and x equals 2. Okay, so that's how we could solve that equation for f of x equals 99 if we didn't have the table and we were just using the equation. Finally, because I want to have you spend time, we can do, let's suppose we have the equation, but we have the graph, or we only have a graph of the equation. I blew this up because you can't see the points on your paper. So if we just had the graph with each of the individual coordinates available, and I asked you to evaluate f of 4, how would you do it? Where would you go? F of 4, what would you do? Look where the input is 4. So I'd look along my x-axis at 4, and then what would I do, Gina? I'm going to go up until I intersect the graph at x equals 4. Oops, I've got to move that over a little bit. Come on, get over there. Come on. Don't waste my time. Come on. There we go. And where I hit the graph is at what height? 460. I know, even when I blew it up, I'll have to get a better picture for next time. So f of 4 equals 67. So a vertical line will give you the output value when x is 4. Now what about this next one? Use the graph to find all solutions. That's interesting. It's plural. To f of x equals 67. How would I approach this one? William? Go up to the y, 67, yeah. Run a horizontal line, right across. And there are your two answers, 1 and 4. So f of 1 equals 67 because the point 167 is on that graph. And f of 4 equals 67 because the point 467 is on the graph. Okay, so there's two answers for that one. So what I'd like you to do now is to work on your group activity. I'd like you to do one from each one. Do one from number 1, one from number 2, one from number 3, one from number 4, so I can make sure you understand each representation. And then if you have time, we'll go back and fill in the rest. Okay, so I want you to try one of each question. Okay, so I'm just going to continue to record this because, as you know, you have a test light and a test heavy grading component, grading option. And the reason I'm showing you this is the green is totally in your control. So if you test light, you have total control over 30% of your grade by doing your projects and doing your homework. Test heavy, you got 10%. But you're pretty confident in your test taking abilities. What I want to point out today is that for each one of these percentages, you only have one assessment. You have one exam. So if you test light, that one exam is counting for 40% of your grade versus in the end, it's 40 divided by 3. It's like 13 and a third percent, right? And if you test heavy, it's counting 16 and what, 2/3 or whatever it is. So remember, you can be really elated when you see a grade or you could be a little dejected, but remember, it's only because you've had one assessment. However, I have to say, I've been here 32 years. I know I don't look that old, but no, I've been here 32 years. I've never had, anytime I've taught Math 107, a class where there wasn't any failing grades. And you are my first class to do that. So give yourself a hand. Woo! It's great news. You did excellent. The median grade on this test was an 88, which means half of you did better than that. There were lots of A's and B's, and there were a couple of grades that weren't as high as others, but overall the class did very well. So you're doing something right, so keep doing it. Okay, it's working. If it's working for you, great. These are in alphabetical order, not highest to lowest. I used to hate that when I was in school and teachers used to start, you always know that the first ones were the best. It's like talk. Yeah, terrible, huh? Really?